Category O, Lecture 7, BGG resolution. Recall that we work with a semi-simple finite-dimensional complex Lie algebra G with a fixed triangular decomposition. G is equal to the direct sum of the negative part and minus, the Cartan subalgebra H, and the positive part and plus. And we denote by W the while group of the root system in H star, which corresponds to our choice of our Cartan subalgebra H. So we consider the associated BGG category O, which consists of all finitely generated G modules, the action of H on which is diagonalizable, and which are locally finite with respect to the action of the universal enveloping algebra of n+. We consider also O0. This is a principal block of O, which is defined as the indecomposable block of O, containing the trivial G module L0. And we already know that simples in this block are indexed by elements of the while group. So for an element W, we denote by LW the simple highest weight module with the highest weight W dot 0. So here dot is the dot action of the while group, that is the action which is shifted by minus rho, where rho is the half of the sum of all positive roots. So similarly, to simplify the notation, we denote by delta W the Fermat module with highest weight, W dot 0, and by PW the indecomposable projective module, which is the indecomposable projective cover of LW. Also recall the following facts about the Fermat modules. For any two elements x and y in the while group, the dimension of the homomorphism space from delta x to delta y is at most 1. Each non-zero homomorphism between delta x and delta y is an embedding, and such a non-zero homomorphism exists if and only if x and y are comparable with respect to the Bruhat order on W. So let us discuss some combinatorial properties of subwords in the while group. So in what follows, we denote by this symbol the Bruhat order on W. Recall the following subword property. For two elements x and y in the while group W, and a fixed reduced expression x into a product of simple reflections, we have that x is greater than or equal to y with respect to the Bruhat order, if and only if there is a reduced expression of y, which is a subword of the reduced expression of x. Consequence, if we have two elements x and y in W, which are related in the Bruhat order, and such that the length of x is equal to the length of y plus 2, then if we denote by AXY the set of all W in W, which are strictly bigger than y, but strictly smaller than x with respect to the Bruhat order, we have that this set contains exactly two elements. And each element W in this set has the property that its length is exactly the length of y plus 1, which is the same as exactly the length of x minus 1. In the subword property, we see that the difference between x and y are two letters. So to get an element from AXY, we can add one of these two letters. And we will denote by x arrow y the property that x is greater than y with respect to the Bruhat order, and the length of x is equal to the length of y plus 1. A claim. To each pair x, y, where x is connected to y by an arrow, one can assign a sign, plus or minus 1, such that for any pair of elements in W, which are connected in the Bruhat order, and such that the difference of their lengths is 2, we have that the product of the corresponding signs for all four arrows between these two and the two intermediate elements is equal to minus 1. Pictorially, we have that if we have two elements A and B, such that they are connected with respect to the Bruhat order, and the difference between their lengths is 2, then we have two intermediate elements U and V, and so we have such a square where we have exactly four arrows, and the product of signs on all these arrows must be -1, which means that the path via one of these elements is equal to the minus pass via the other of these intermediate elements. For example, consider the symmetric group S3, which consists of the identity element E, two simple reflections S and T, their products ST and TS, and then the longest element W0, which is equal to STS or TST. Then we have the following graph of the Bruhat order. So this is the Hasse diagram of the Bruhat order for the group S3. And if we choose the signs as shown on this picture, the property as discussed in the previous slide is satisfied. So we choose ones only for two vertical arrows between ST and S and between TS and T, and all other signs we choose to be -1. So if you take, for example, this square, then we have ST to S to E has the sign -1, while ST to T to S has the sign -1 times -1 is 1. And we can check that each square in this picture contains exactly 1 and 3 -1s. So the product of the numbers over all edges of the square is -1. Now let us prove this claim under an additional assumption. Let us assume that we can fix a reduced expression for each element in W at the same time, such that the condition that x is greater than or equal to y with respect to the Bruhat order is equivalent to the conditions that R of y is a subword of R of x. So in this case, we define the sign epsilon xy for x arrow y as -1 to the power I, where I is a position of the letter which one has to delete to get R of y from R of x. Now we assume that we have two elements A and B, which are related in the Bruhat order, and the difference of lengths between which is 2. Then, to get from the reduced expression of A to the reduced expression of B, we need to delete two letters. Let's say that they are in the positions I and J, where I is smaller than J. And know that if we first delete the I's letter, then the letter in the position J changes the position, and the new position will be J -1. This immediately applies our statement because, according to our definitions, one way in our square will be -1 to the power I times -1 to the power j. This is when we first delete j and then delete I. And in the opposite way, it will be -1 to the power I times -1 to the power j -1. And these two products are related by a sign. For the full proof, I refer to the original paper of Bernstein, Gelfand, and Gelfand, which is called Differential Operators on the Base Affine Space and the Study of G Modules. So now, with this combinatorial lemma at hand, we can define what is known as a BGG complex. For an element W in W, we identify delta W with its image in the dominant Verma module delta E. So there is a unique submodule of delta E, which is isomorphic to delta W, and we just identify delta W with the submodule of delta E. In particular, for each x and y related in the Bruhat order, this defines the canonical map, which we denote by phi xy, from the Verma module delta x to the Verma module delta y, since both are now realized inside delta E. And of course, directly from the definition, we have that if x, y, and z are related in the Bruhat order, then the composition of phi xy with phi yz is equal to phi xz. This follows directly from the definition. Now, for each non-negative integer I between 0 and the length of the longest element in W, We denote by W sub I the set of all elements in W of length exactly I. And again, for each such I, we denote by M sub I the direct sum of all Fermat modules delta W, where W is in Wi. If we have two elements x and y in W, such that the length of x is I and the length of y is I minus 1, and which are not arrow related, then we define the corresponding phi xy to be 0, and the corresponding sign epsilon xy to be 0 as well. Define the linear map D sub I from mi to mi minus 1 using the following matrix. So it's a matrix where the columns are indexed by elements in Wi and rows are indexed by elements in Wi minus 1. And the element in the intersection of the row indexed by y and the column indexed by x is exactly epsilon xy times phi xy. So phi is our canonical map, and epsilon is our sign, which was chosen using the previous lemma. The claim, if we now consider the sequence which consists of all these mi's and the linear maps di's between them, then this sequence is a complex, and this complex is called the BGG complex. And the claim that the sequence is a complex just means that the composition of two maps in the sequence is 0. And the fact that the composition of two maps in the sequence is 0 follows directly from our properties of the sign. So the composition of two maps corresponds to adding up the two different ways to go from the module delta x to the module delta y, where the lengths of x and y are different by 2. And since the two different ways have different signs, in the sum they will cancel. So this follows directly from the properties of our objects. For example, consider the Lie algebra SL3, in which case the corresponding while group is S3. So it has 6 elements, one element E of length 0, two elements S and T of length 1, two elements ST and TS of length 2, and one element W0 of length 3. Then the corresponding BGG complex looks as follows. So we have delta E on the right, then delta S plus delta T, delta ST plus delta TS, and delta STS, with the linear maps D1, D2, and D3 between them, where the map D3, so this is a map from delta STS to delta ST plus delta TS, consists of minuses of the canonical inclusion. So this is because of, here is our choice of signs. This is -1, from STS to ST and TS. Then from ST and TS to S and T, we have 1, -1, -1, and 1, and -1 on the upper level. So we have two minuses here. Coefficients 1 in the map D2 for phi's from ST to S and from TS to T, and all other coefficients are -1. And this corresponds to our choice of the signs in the Bruhat order graph. Okay, now we can formulate the main result, which is known as the BGG resolution. So the claim, which is due to BGG from 1971, is that the BGG complex constructed above is a resolution of the trivial G module LE. In other words, the homology of this complex at position 0 is isomorphic to LE, and all other homologies are 0. So this complex is exact at all other positions. So in the position 0, by definition, we have the quotient of the dominant Fermat module delta E by the sum of all submodules of the form delta S alpha, where alpha is a simple root. We have already seen earlier during these lectures that this quotient is a simple finite dimensional module, which thus must be LE, because this is a quotient of delta E. So the claim about position 0 we already know. What remains is to explain why this complex is exact in all other positions. So the full proof of this can be found in the original paper of Bernstein-Gelfand already mentioned above, and there is also a relevant paper by Rocha-Caridi, which also takes a slightly different view and proves slightly different results about the BGG resolution. So the paper of Rocha-Caridi is in Transactions of the IMS from 1980. So let's give a general explanation, a hand-waving general explanation for the exactness of this complex. For this, we need to recall a little bit about the Lie algebra cohomology. So let A be a Lie algebra and S a Lie subalgebra of A. Consider the S module A quotient by S, and let overline denote the canonical projection from A to this quotient. For a non-negative integer k, denote by nk the following space. So it's a tensor product of UA over US with the k's external power of the vector space A divided by S. Then we can define the differential, the linear maps between nk and nk minus 1 in the following way. So dk applied to x tensor product with the wedge of x1, x2, and xk is the following very big sum. So sum over I from 1 to k, the sign minus 1 to the power I plus 1, then x multiplied one with yi. So yi is a representative of xi. So xi is in the quotient space. Yi is any representative of xi in the original algebra A. And then tensor with the wedge, where the ith component of the wedge is deleted. The idea what we do here, we take the ith component, we commute it all the way to the tensor product, and then move over through the tensor product. During this process, we do I minus 1 commutations. So this is the reason for the sign minus 1 to the power I plus 1. So the sign of I plus 1 and I minus 1 are, of course, the same. And then plus, so this is the first summand, this big sum, and then the second big summand, similar sum over all I smaller than j. We take elements and positions xi and xj, commute them all the way to the left, then take the Lie bracket of their representatives and then apply the overline to this Lie bracket. This gives us, because of the commutation, the sign minus 1 to the power I minus j and this expression. So as already mentioned, yi is some representative in A of xi, which belongs to the quotient space. And the standard fact from the Lie algebra cohomology is that this complex is a resolution of the trivial A module. So now we can use the idea of this relative cohomology to prove or to explain exactness of the BGG resolution. So we consider the relative Lie algebra cohomology for the pair G and the Borel subalgebra B. Note that the quotient G over B is isomorphic to n minus as an H module. In particular, the case exterior power of G modulo B is isomorphic to the case exterior power of n minus as an H module. Also observe that the element of the relative cohomology complex UG tensor over UB, the case exterior power of G mod B, belongs to the category of modules having Verma flag because of our PBW theorem. So this is a finite dimensional B module, and we take the free induction to UG. This module has a Verma flag. Also note that this module, it belongs to category O, but it has a lot of summands which lie outside of the trivial block O0. So what we can do, we can take this relative cohomology complex and project it onto the trivial block of category O. And then one compares the projected complex from the relative cohomology with the BGG complex and uses the exactness of the first one to establish the exactness of the BGG complex. And for the full proof, I refer to the original paper of BGG. The full proof with all details is not short. So let's consider the SL3 example. So in this example, the basis of the root system consists of alpha and beta, And the dot orbit of 0 consists of the weights 0, minus alpha, minus beta, minus alpha minus 2 beta, minus 2 alpha minus beta, and minus 2 alpha minus 2 beta. So the support of the 0 exterior power of n minus is of course 0. The support of the first exterior power of n minus is the support of n minus, which is just the set of all negative roots. So this is minus alpha minus beta and minus alpha minus beta. The support of the second exterior power of n minus is of course the set of all sums of different negative roots. So this is minus alpha minus 2 beta, minus alpha minus beta, and minus 2 alpha minus beta. Finally, the support of the third exterior power of n minus consists of the sum of all negative roots, which is minus 2 alpha minus 2 beta. So the relative cohomology complex will have the following form. So it starts from 0, then we go to delta minus 2 alpha minus 2 beta, then to the sum of 3 deltas with weights minus alpha minus 2 beta, minus alpha minus beta, and minus 2 alpha minus beta. Then the sum of deltas for minus alpha minus beta, and minus beta, then delta 0, and then 0. Note that the weight minus alpha minus beta, which appears in the relative complex, is not in the dot orbit of 0. So therefore, these summands, they lie outside dot 0 and can be just thrown away from our resolution. And we see that the O0 part of the relative cohomology complex is more or less exactly the original BGG resolution. So the BGG complex in the case of SL3 has this form, and component-wise it's the same as this cleaned up relative cohomology complex. Okay, so now we can use this BGG resolution of the trivial module to compute the global dimension of category O. So the theorem, which is from the original paper of BGG on category O, that the global dimension of category O equals twice the length of W0. In one direction, we need to prove that any object M in O has projective dimension which is at most twice the length of the longest element in the while group. Since every module has a composition series, it is enough to show that the projective dimension of any simple module is bounded by twice the length of W0. In the first step, we prove that the projective dimension of any Fermat module is bounded by LW0. We define the depth of the Fermat module delta lambda as the maximal K for which there are proper inclusions of delta lambda, which is as delta lambda 0, into a different Fermat module delta lambda 1, and this is included into a different Fermat module delta lambda 2, and so on, all the way up to delta lambda K. And from the BGG theorem, it follows that the depth of delta lambda is at most the length of the longest element in the integral while group of lambda, because each such inclusion is when we reflect with respect to some root in our while group, and we get an element which is smaller with respect to the partial order on the set of all weights. In terms of the while group, this corresponds to the Bruhat order, and Bruhat order being a subword order, so elements which are related in the Bruhat order have different lengths. Bigger element must have bigger lengths. So this means that the length of the chain of elements in the Bruhat order has lengths at most the length of the longest element. So we will need this to explain the property that the projective dimension of a Fermat module is bounded by the length of the longest element in the while group. So now let's prove this. Recall that the indecomposable projective P lambda surjects onto delta lambda, and the kernel of this surjection is filtered by Fermat modules of strictly smaller depths. Here we use the BGG reciprocity. So in particular, depth 0 Fermat modules are exactly the projective Fermat modules, again by the BGG reciprocity, because the corresponding projective module cannot have any other deltas in its Fermat flag. So using the homological dimension shift, we thus conclude that the projective dimension of the Verma module delta lambda is bounded by the depth of delta lambda, and this is bounded by L of W0. So we can do the induction here. We have a kernel which is filtered by deltas of strictly smaller lengths. So we do the usual homological dimension shift, which tells us that the delta lambda, which has strictly bigger lengths, has projective dimension at most the maximum of projective dimension of smaller guys plus 1. In step 2, now from this property we deduce that the projective dimension of the simple module L of lambda is at most twice the length of the longest element minus depth of delta lambda. And this is of course bounded by twice the length of the longest element. Again, we do induction on the depth of delta lambda, and the maximum depth means that the delta lambda is simple. So we can use a step 1 and say that for the maximum depth, the projective dimension is at most L of W0, so this formula is okay. And then we use induction on the depth of the Verma module. So the Verma module delta lambda surjects onto L lambda, and the kernel is filtered by simple modules which have strictly greater depths. So now we can use again the homological dimension shift, that the projective dimension of this L lambda is at most 1 plus the maximal of projective dimensions of guys with strictly smaller depth. So combining these together, we get that the projective dimension of all simple modules is bounded by 2LW0, and this proves one direction of our global dimension theorem. Each module in O has projective dimension at most twice the length of the longest element in the while group. For the other direction, we will use the BGG resolution. So we claim that the trivial module LE has projective dimension twice the length of W0. More explicitly, we claim that the X of degree twice the length of W0 from LE to itself is non-zero, namely it has dimension 1. To prove this, we apply the simple preserving duality on O to the BGG resolution, which we denote by BGG, of the trivial module which we constructed before. So this gives us a co-resolution of the trivial module. So the trivial module is of course self-dual because the duality is simple preserving. So we get a co-resolution of the trivial module by dual Verma modules. So this is our co-resolution. And we also already seen that Verma modules and dual Verma modules are homologically orthogonal to each other. So the all non-trivial X from Verma modules to dual Verma modules vanish. This means that in order to compute the X of degree 2LW0 from the trivial module LE to itself, this X is isomorphic to the homomorphism space in the homotopic category of O from the BGG complex to the dual BGG complex shifted by 2 times LW0. So this is because the components of the BGG complex are deltas, the components of the dual BGG complex are nablas, and they are homologically dual to each other. Also observe that the leftmost component in the BGG complex is exactly the simple Verma module delta W0, and because the duality is simple preserving, this is isomorphic to the dual Verma module, nabla LW0. So therefore, we can consider our BGG resolution, so here it is, and we consider the dual BGG resolution, so BGG co-resolution, here it is. It is shifted by the twice the length of W0. So this complex has the cohomology LE here. This complex has the cohomology LE here. And now we take the identity map from MLW0, which is just simple LW0, to MLW0 star, which is again the same LW0. We have this identity map, and this identity map is clearly a homomorphism of complexes, because it gives us 0 here and 0 here. All other maps are 0 because there is no other choice. And also note that this non-zero map between complexes gives us a non-trivial morphism in the homotopic category because there are no morphism from this component MLW0 to M star LW0 minus 1, because this consists of delta W0 and this consists of nabla W, where length of W is LW0 minus 1. So there is no W0 here. Similarly, here are deltas for elements which have lengths LW0 minus 1. There is no W0 here, and this is nabla W0. So there are no homotopies in this picture, which means that this gives us a non-zero map of complexes in the homotopy category, and hence a non-zero X of degree 2 LW0 from LE to LE. Using similar arguments, one can show that the dimension of the space of all extensions of degree 2k from LE to LE is equal to the cardinality of the set WK, so where k is a non-negative integer. So far we have constructed the BGG resolution of the trivial module, but this can be easily extended to all simple finite dimensional modules. So let's take now an integral dominant and regular weight lambda, and this is exactly the case when the corresponding simple highest weight module L lambda is finite dimensional. Denoted by mk the direct sum of all Verma modules of the form delta w dot lambda, where w is an element of wk. So here k is a non-negative integer. So define the linear operators dk from mk to mk minus 1, similarly to the case lambda is equal to 0. And then the claim is that the corresponding complex which we obtain is a resolution of the simple finite dimensional module L lambda. And the sketch of the proof is as follows. We take the BGG resolution of the trivial G module and apply to it the exact functor of tensoring with the simple finite dimensional module L lambda, and then project the outcome of this resolution onto the block of O which contains L lambda. One can check that this projection will be exactly this complex. So this gives us the general BGG resolution of a simple finite dimensional G module in terms of Verma modules in category O. So let's conclude with some questions for PhD students. Question number 1. For the Lie algebra SL3, check that the BGG resolution of LE is a resolution of LE by Hence, using what we know about the characters of simple and Verma modules in this case. Question number 2. How can one use the BGG resolution to simplify parts of the proof of the Weil character formula from the previous lecture? Question number 3. Compute the dimension of the extensions of all degrees from the trivial G module to all dual Verma modules, and the dimension of the extension spaces from all Verma modules to the trivial G module. Prove that the projective dimension of LW0 is equal to the length of W0. And question number 5. Construct by Hence in type A3 the assignment of the signs to each pair x arrow y, which has the properties as required in the construction of the BGG resolution. Thank you very much. See you next time.